Can we see my slides?
Yes.
All right. Sorry for not being able to speak with my microphone earlier. I'm Tammas Loughran. I'm a postdoc at CSIRO, working on carbon dioxide removal strategies and the impacts that they have on the climate and the carbon cycle. And today I'm going to be talking about, I'm not really going to be showing any access biases in response to land use change per se. I'm just going to be showing some unexpected results that I had of some simulations that I was looking at. And so I guess the motivation of this work is that I was doing some stuff on forestation and seeing how much CO2 it could remove and what the impacts on climate were. So I'm going to be focusing mostly on the temperature response to changes in land use. So I guess while growing forests can reduce global temperatures biogeochemically through reduction of atmospheric CO2 concentration, no one's going to want to grow the trees if they cause localized warming with increased albedo. So we can use models to sort of figure out, okay, what's the projection going to be relative to biogeochemical responses in the future. To start, I'm just going to give an overview of the basic ideas of how climate responds to land use change effects. And I'm going to show a few observations. I won't link it too long, mostly regarding deforestation, because in the past, that's what has occurred. And then I'm going to sort of explain that, comparing the observed response and what we see in models is not entirely fair because models have a non-local component to them. And then I'm going to show you some of the results that I've been looking at with ACCESS in response to forestation specifically. So I'm sort of going to be going back and forth between deforestation and forestation. So this is the basic idea of how land use change affects climate or temperature specifically. So when you go from a forest to a non-forest, say crops or whatever, it really depends on the specific land cover type that you're transitioning from and to. But the basic idea is that you're changing surface properties such as albedo, the roughness, the leaf area, and the water availability. That then affects various processes. So changes in albedo affect the radiation absorption and the radiation balance. Changes in roughness change the evapotranspiration and the turbulent heat fluxes. And so usually at the low latitudes, what this means is that the surface roughness and the turbulent heat fluxes usually dominate over the changes in albedo. So as you have deforestation, it causes an increase in temperature as you go from forest to non-forest. But the relationship is sort of reversed at the very high latitude, so the boreal regions. So usually what happens is that, at least for part of the year, the ground is partially covered in snow, and so you have lower leaf area at higher latitudes, and so the changes in the turbulent heat fluxes aren't quite as important. And so the albedo effect dominates, and so with deforestation, you usually have cooling. So yeah. And so the reverse, in theory, is true for forestation as you're going from non-forest to forest. Generally, that forestation at the higher latitudes causes warming, and in the low latitudes it causes cooling. And so these are a few examples of some of the observations, and I don't really want to go into detail about what they are and so on. I just want to show you that on the left we've got the deforestation results, and they all seem to be fairly consistent. The low latitude regions, there tends to be this sort of warming with deforestation, and at the high latitudes there's this cooling. And then the opposite for the forestation example that I have here. There's cooling for forestation in the tropical regions and forestation in the high latitude, the boreal regions generally causes warming. So these observed changes are really only the local response of the climate to land cover change. There's also non-local effects on the climate. So if you have changes in surface properties, then the changes in the climate response can then be affected downwind. Heat and moisture can be transported elsewhere, and also these changes in surface properties can alter the atmospheric circulation. So these are typically known as atmospheric feedback effects. And when you're looking at observations with different, usually what you do is you have a site with, say, if you're using satellite data, you might look at a pixel with forest cover and a nearby pixel without forest cover and compare the two. But when you do that, you're sort of cancelling out the non-local effects. So yeah, observations are local only, whereas if you look at models, it's including both the local, the non-local effect, and also the biogeochemical effect from changes in atmospheric CO2. So this is from a paper that I've been working on forestation scenario. Basically is a high emission scenario where I've compared the SSB 585 to a similar simulation that has the SSB 126 scenario, which typically has forestation in it. And so you take the difference of the two, and these are all of the models that I've looked at except ACCESS, and they're really quite all over the place when you consider all of the local, non-local, and biogeochemical effects together. So it's really sort of difficult to compare this to the observations. Quite a few models have the typical response of like this sort of cooling in the tropical regions with forestation, but there are a few models that really don't sort of follow the trend, and ACCESS is one of them. So I sort of this is a correlation between the change in tree cover fraction and the air temperature. And so there's some regions that have some cooling and some regions that have some warming. And these regions where there's a lot of forestation occurring in this scenario typically have warming in the tropical regions, which is sort of surprising. And so the idea that I've sort of come up with is that, okay, perhaps the albedo is overrepresented, the response to albedo is overrepresented, or perhaps cable doesn't really represent the turbulent heat fluxes as well. So in response to this, I decided to do some really simple sensitivity experiments relying on the global warming level simulations. So if you cast your mind back a few days ago to Thiele's talk, who introduced these simulations, basically it's the goal was to try and stabilize the climate at different global warming levels. So for example, the simulations are branched at certain points along an SSB 585 scenario at different points in time, and then run for a very long time without emissions to try and get a stabilized climate. So I think the 2035 branching point here is an example of a climate that's consistent with the 1.5 degrees target that we're aiming for with the Paris Agreement. So I used these simulations as a baseline, and I said, okay, let's get rid of all of the crops and replace them all with trees. So let's kick the model at different global warming levels to see how it responds. And this is the change in CO2 from this change in tree area. So on the left here is the just the first year of these experiments, and on the right is the last 30 years of these experiments. So the left has just the local and the non-local response, and the change from the immediate locations of forestation are really quite obvious. So they match very well with this pattern here. And then the additional biogeochemical cooling is on the right here. So yeah, I guess this response at higher latitudes of forestation is sort of expected, but the unexpected parts are these regions where I would typically expect cooling. Biogeochemically, there's also an unexpected result in the soil carbon, and I understand that soil carbon is really difficult to get right, but with the Lumit forestation scenario, when I was comparing to other models, one of the unique features of ACCESS is that soil carbon tends to decrease as you change from non-forest to forest. And typically you would expect that, oh, well, if you're going from transitioning to a forested PFD, you would expect that there would be more litter, and that this litter would trickle down into the soil pools, and so you would end up with more soil carbon. And that's what most models show, but ACCESS is not. The other one that shows a decrease in soil carbon is the UKASM. I think this is purely by coincidence, because based on the conversations that I've had with them, it's for a completely different reason in this scenario. So with the sensitivity experiments, I also plotted the carbon pools to try and figure out what's going on with this decrease in soil carbon. So these lines down here are the soil pools, and these two groups of lines are the litter pools. And so carbon tends to just sort of accumulate in the litter pools in ACCESS rather than sort of going into the soil. And I'm sort of assuming that the respiration rates in the litter pools are higher. But I haven't really looked at this in much detail yet. So yeah, I guess the point of my talk was just to sort of open this discussion of what might be going on in these models. So to summarize, basically deforestation causes low local warming in the tropics and cooling in boreal regions, and it's expected that forestation causes the opposite. When comparing to observations, the observations are only the local effects, and they don't include the non-local and biogeochemical responses. Yeah, and that there's these two unexpected results that I've had. So thank you for listening.